Hi guys, hi everyone. This is D Pranay Kumar from CSCC section. So now let's discuss. Today's topic is a unitary matrix pencils in signal processing. So first let's know about the unitary matrix. What is unitary matrix? A unitary matrix is a matrix whose inverse equals its conjugate transpose. That means A inverse equal to A. Suppose let's take A is a matrix. So A inverse equal to A. Unitary matrices are the complex analog of real orthogonal matrices. If a unitary matrix is a square or complex matrix, then the following conditions are equivalent. The conjugate transpose A equal to A inverse. So now let's look into the unitary matrix. What is a unitary matrix? The detailed composition. So in linear algebra, a complex square matrix unitary is the conjugate of transpose of another unitary matrix, and also its inverse. That is, if A inverse into A equal to A into A inverse, that is I. So now let's look into those. Let's look into the properties of a unitary matrix. For any unitary matrix, let's take the matrix as A. For any unitary matrix A of finite size, these following properties will hold. So, given two complex vectors x and y, multiplication by a unitary matrix preserves their inner product, that is ax comma ay equal to x comma y. If A is diagonalizable, then A is the unitarily similar to the diagonal matrix as a consequence of the spectral theorem. Thus, A has decomposition of the form A equal to V D V transpose, where V is unitary matrix and D is diagonal and unitary. So, mod det of a unitary matrix is equal to 1. Its eigenspaces are orthogonal. A unitary matrix can also be written as a u equal to e power IH, where e indicates the matrix exponential and I indicates the imaginary unit and h indicates the Hermitian matrix. For any non-negative integer n, the set of all n cross n unitary matrices with matrix multiplication forms a group called the unitary group. For any square matrix with unit ecloidal norm is the average of two unitary matrices. So let's look into the equivalent conditions of a unitary matrix. So if U is a square if U is a square complex matrix, then the following conditions are equivalent. U is unitary and U transpose is unitary. U is invertible and U inverse is equal to U transpose. So the columns of U, that means unitary matrix, form an orthonormal basis of C power n with respect to the usual inner product. In other words, we can also tell it as U transposed into U equal to I, which is equal to the identity matrix. The rows of U from the orthonormal basis of C power n with respect to the usual inner product. In other words, we can call it as U into U transpose equal to I. That means identity matrix. U is a normal matrix with eigenvalues lying on the unit circle. Elementary constructions. For a 2 by 2 unitary matrix, the general expression of the matrix is U equal to A B of A minus E I phi B transpose E I phi A transpose. These are the eigenvalues. So now let's look into the next topic. So now let's start about the how the unitary matrix are used in the signal processing. Unitary matrix pencils, how they are used in the signal processing. Now let's see the introduction first. So a fundamental problem in signal processing is the approximation of a discrete time sign, that means sk. We can simply call it as sk. K belongs to the n, that means natural numbers, but the sum of potential, that is sk, is simply equal to or similar to sigma pj. This you can see now, omega j e power I theta jk, k equal to 0, 1, 2 and so on. This problem is known as the or retrieval by harmonics. The frequencies and amplitudes are often determined such as the term. Yeah, you can see the equation below, right? This one, this equation, that is sigma j equal to 1 to p mod omega j whole square e power I theta j power k. Match approximations of the rest and autocorrections lags, that is ik equal to sigma minus infinity to infinity s j bar into s j minus k equal to 0, 1 and so on until n minus 1. So now let's look into the next slide. So first one, the Toeplitz matrix Tn built with these Tk is called the autocorrelation matrix of order n, and the problem can thus be viewed as the problem of approximating the entries of the autocorrelation matrix Tn in a suitable way. Typically, such an approximation is constructed via solving a linear system Tn x equal to b, or via modifying Tn to a singular Toeplitz matrix, that is T similar to n, and computing a vector in its null space. The frequencies j and then are computed from x, or it can be shown, however, that the approximations can directly be derived from the solution of a unitary eigenvalue problem 365. For example, let's take it. The basic observation is that any Hermitian positive definite Toeplitz matrix Tn for dimension n has the Chokles decomposition. That is, you can see this, right? Tn equal to I naught of e1 comma h of rho e1 and so on until h power n minus 1 of rho e1 power h. Yeah, this one, where h rho equal to h of gamma 1 to gamma n minus 1 comma rho is an n cross n unitary Heisenberg matrix, is parametrized from the form, and the parameters r k power n minus 1 into 1 are the pseudo parameters from the Levi's theorem applied to the Tn comma rho, is an arbitrary number on the rk of n minus 1 is a singular parameter unit circle. The frequencies theta j can essentially be computed from eigenvalues of such a unitary Heisenberg matrix. The amplitudes omega j, which are given by the ways. The first components of the corresponding eigenvectors normalized to be real and non-negative. Thus, for the computation of the approximation, we can use the reliable and efficient eigenvalue methods available for unitary. So, then let's look into the next slide. So, this is the theorem 1. Now, let's look into the theorem 1. Yeah, this is the question. Let's read it. Let h equal to h of gamma 1 to gamma n minus 1 comma rn be the unitary Heisenberg matrix. Let g0 minus lambda ge be the skew parameter pencil built from the same skew parameters gamma 1 to gamma n minus 1 gamma n and the related complementary skew parameter then the matrix pencil G naught minus lambda GE has the same eigenvalue and weighs as H. See, you can look into the proof given below. First column, forming matrix Q is Q power H into HQ equal to G naught into GE power H, which is the first unit vector, and the statement following immediately from studying the spectral decomposition of H and G naught G H power E. The unitary QR algorithm applied to the unitary Heisenberg matrix, as can be concluded from the following theorem. Yeah, now it's theorem 2. Let H equal to H of gamma 1 to gamma n minus 1 comma gamma n be the unitary Heisenberg matrix, and G naught minus lambda GE be the skew parameter pencil built from the, yeah, this is the same way how to do the, as you have seen in the theorem 1, same way you have to do in the theorem 2, the another example. That's it. Next, error bounds. So solving the retrieval of harmonics via a unitary eigenvalue problem also has the advantage that we can make use of the mathematically rich eigenvalue structure of unitary matrices. This allows in particular to give bounds on the distance of the computed approximations to the frequencies to the actual frequencies 3 comma 1. The basic result is as follows. Yeah, now let's look into the basic result here. Now let's look into the third theorem. Let unitary matrix belongs to C n cross n be unitary, and Q1 belongs to C power n with mod Q square equal to 1. Assume that n steps of the isometric Arnoldi method applied to U have produced the skew parameters gamma 1 to gamma n and the corresponding complementary skew parameters sigma 1 to sigma n. Let C equal to gamma n by mod Rn, and consider the unitary Heisenberg matrix H equal to H of gamma 1 to gamma n minus 1 comma C, or the corresponding skew parameter pencil. If we denote the eigenvalues of H or skew parameter pencil by mu 1 to mu n and eigenvalues of unitary matrix by lambda 1 to lambda n, then for I equal to 1 to n, I equal to 1 to n, ij belongs to minimum of set 1 comma n natural numbers mod mu I minus lambda j less than equal to under root of sigma n square plus mod minus Rn whole square. Moreover, there is a permutation pi of 1 to n such that for each I belongs to 1 comma k. Now let's look into the theorem 4. Theorem 4 consists of, with the notations above, the following holds: J belongs to minimum of set 1 to n mod mu 1 minus mu lambda j less than equal to mod s n I under root sigma n square plus mod Rn whole square. The mu I as well as the lambda j are on the unit circle and have therefore a representation as e power I theta I bar and e power I theta j respectively. Therefore, the bound above also gives the bound for the distance of the frequencies theta I to theta and theta j. If we study the theorem especially for U as the n cross n downshift matrix, J for the normalized signal vector S equal to S1 comma Sn, S1 to Sn as vector Q1, then the theta I are the approximations to the desired frequencies derived with the method described in the beginning, and the theta j are the frequencies in the exact representation of the signal S equal to S1 comma Sn, and theorem 4 provides us with the estimate of the correctness of the approximation of the form. Yeah, you can see the equation given below. Next, at last, we can conclude that the unitary matrix, this is how the unitary matrix pencils are used in the signal processing, which is very useful for the today's life. Thank you.